Hello guys, welcome to thermodynamics lesson enthalpy. This is a review from our previous unit. So we're going to review the first page, which is just a whole bunch of vocabulary from unit 2. And so the first thing that it says is change in internal energy. And change in internal energy is often represented by change delta, which is the triangle, capital E, and then INT. The other way that you can represent internal energy is delta U. They're the same thing. It is important to define the system, that's what we're looking at, versus the surroundings, because if you define the system as the surroundings, then the positive and the negative signs will be flipped. So make sure the first thing you do for any thermodynamics question, any thermochemistry question, you have to define your system first, your surroundings second, so that way you have your positive and negative signs correct. All right, the movement of matter between systems and surrounding in an open system is possible. The movement of energy between system and surroundings in an open system is also possible. An open system, think of that as like an open beaker, right? It is open to the atmosphere, is open to the room. Things can go into it, things can go out of it. So for example, movement of matter in an open beaker, you have water in this beaker. Water particles can evaporate, but they can also condense back into the beaker. So things can go in and out, energy can go in and out. In a closed system, think of that beaker in a box now. So matter can't move in or out of this closed system, right? Like nothing can escape this box, nothing can enter into this box. But energy can move in and out of the surroundings, right? So energy can go around this box, it can go in the beaker. So energy can move in and out, but matter itself cannot change. So we can't add anything to it because it's in a box. Can't take anything out of it because it's in a box. All right, an isolated system, that is something like you have something in a beaker in a box and there's a lid on top of that beaker. So no matter can move in and out of the surroundings. No matter can move in and out, or energy can move in or out of the surroundings in the system. So the system in this case, if I didn't define it, was the beaker. The surroundings was anything on the outside. So in the open system, the surroundings was the environment, the room. For the closed system, the surroundings was the box that the beaker is placed in. And for an isolated system, the surroundings would still be the box, but there's a lid on top of that beaker, so nothing can interact with that system or with that surrounding. All right, moving down to the next part. Internal energy, or EINT, of a system is the sum of all the kinetic energy which contributes to the temperature and the potential energy from attractions of particles. I would definitely make sure you know those definitions, know the definition of internal energy, know the definition of kinetic energy, and know the definition of potential energy. Kinetic energy is often abbreviated as KE. Potential energy is often abbreviated as PE. The first law of thermodynamics states that in an isolated system, one in which no matter or energy can be exchanged, the internal energy of that system is conserved, right? So in an isolated system, nothing can go in that system, nothing can go out of that system, nothing can go in the surroundings or out of the surroundings. And so then that is when we say that is equal to 0. Nothing is happening, it's just conserved. Energy can be converted from one form or another, such as kinetic to potential energy. Think of it as like a bank account. You have your checkings and your savings. You can get money from your checkings and put it into your savings, or you can take money from your savings and put it into your checkings. That's essentially what kinetic versus potential energy does. But the total energy cannot increase or decrease. So this is the first law of thermodynamics. In big summary, says that we can't create energy, we can't destroy energy. The energy of the entire system has to be conserved. So energy can be exchanged from different types of energy, such as kinetic versus potential, but you cannot create it, you cannot destroy energy. This is kind of like the law of conservation of mass. All right. However, no two systems are truly isolated. So the internal energy of a closed system can change in two ways, with heat or work. And so overall, this was our equation that we learned last semester, right? So the internal energy is equal to the heat, which is Q, and work which is W. So if you add those two together, that's the overall energy, internal energy. Heat, Q, is represented by Q equals MCAT. And work, W, is represented by W equals negative P, which is pressure, times the change in volume. So often with these types of thermodynamics problems, if it's a free response problem, part A or B or C, like one of the early parts in the free response question, you might ask to solve for work, and they might give you pressure, or ask you to solve for pressure, or ask you to solve for volume, and you know how to do that because we have pervnert. So if it asks you to solve for work, but it doesn't give you a pressure, or if it doesn't give you a change in volume, you can solve it by using PV equals nRT, and we also have the combined gas law, right? PV over T equals PV over T. And this would be our first one, and then those would be our second one. All right, so we can find it. That's just a heads up. I've seen that before in certain questions. All right, this picture right here was kind of the summary of everything. I would definitely somehow photograph this into your memory. It is a summary of how a system can change, the internal energy of that system can change from work or from heat. So heat, as you guys all know, endo is positive, it's greater than 0. Exo is negative, it's less than 0. Work, if it's compressed, so if you're pushing that piston down, this is the piston right here. If you're compressing it, work will be positive, it'll be greater than 0. And if you're expanding it, so if you're pulling that piston out, it'll be negative, less than 0. So this one right here, commit that picture to memory. All right, moving down to the next part, example number 1. It says a 20-gram sample of argon in a cylinder with a piston at 30 degrees Celsius. Heat flows into the cylinder, increases the temperature to 40 degrees Celsius. The cylinder expands against a constant pressure of 95.5 kilopascals from 21.5 liters to 23.5 liters. By how much has the internal energy of the system changed? Argon has a specific heat of 0.52 joules per gram degree Celsius. And it gives us the conversion from 1 joule equals 1 liter per times kilopascals. All right, pause the video, see if you can underline every valid piece of information that they gave us. What are our next steps? And then I will start explaining it as well. Okay, so we have 20-gram sample of argon. That is an important piece of information that we will need. It says that it was at 30 degrees Celsius, so this is our first temperature. Heat flows into the cylinder and it increases that temperature to 40 degrees Celsius, so it goes from 30 to 40, so we have a 10-degree change in temperature. The cylinder expands, right? We know that if it's expanding, it will be a negative W against a constant pressure of 95.5 kilopascals from 21.5 liters to 23.5 liters. So our change in volume is about 2 liters, I believe. And it asks how much does the internal energy of the system change? So we're trying to find the change of energy. It gives us the specific heat, which is C from MCAT, and it gives us a change of joules and liters, kilopascals. They're the same. It gives us a unit conversion. So the very first thing that we need to do is Q equals MCAT. Right? So we need to find the Q, and we need to find the W. Right? And so W is equal to negative P times delta V. So Q equals MCAT, we have our mass. It was 20 grams sample of argon. So we can plug that in, 20 grams of argon. Our C is our specific heat, which is 0.52 joules per gram degrees Celsius. Our change in temperature was the 40 to 30, right? Our final was 40 minus our initial is 30, which is overall 10. So if we multiply all of that together, our heat comes out to approximately positive 104 degrees, or not degrees, joules, right? And then for work, we have the negative pressure, and so we have negative P, which was 95.5 kilopascals. Our change in volume was 23.5 liters minus the initial, which was 21.5 liters. And when we subtract it and multiply all of that out, we end up with negative 191 joules. All right. We know that because this is positive, it is endothermic for Q, and because this is negative, it is expansion, it's work out. So that makes sense. So the last step that we have to do is just get the change of internal energy, and that's just Q plus W. So by adding those two numbers together, 104 and negative 191, we end up with negative 87 kilojoules. Sorry, not kilojoules, joules. And there you go. So the system lost 87 joules of energy to the surroundings.